In this lecture, we will continue our discussion on quicksort.
At the end of the last lecture, we talked about a very simple sorting algorithm. This sorting algorithm actually forms the basis of the quicksort algorithm. But we still have a problem because we're making extra lists and we're doing recursive calls because we're splitting our array, or I should say partitioning it, into 3 sets. So we're putting all these elements into these newly formed lists, and then if we're doing this recursively, we really haven't made any improvements compared to the merge sort algorithm. So the challenge here is we need to make sure that we cut down the memory that we're using. Let's look at the most common implementation of quicksort, which we call classic quicksort. So our input is going to be an array, which we'll call S, and we're not going to allocate any extra memory, or we won't create any extra arrays. Everything will be done in S. There are 4 steps to this algorithm. The first step is we check the number of elements in S. If it's 0 or 1, then we just return. We're done. If there's only one thing in the array, it's sorted. If there's nothing in the array, well, guess it's kind of sorted, but there's nothing to do. So the other steps are going to assume that there's at least 2 elements in the array. So the next step is we're going to pick some element v in S. And we're going to call this element the pivot. So once we have our pivot, the next step is that we're going to partition the remaining elements in S into 2 disjoint groups. The first group, which we'll call S1, is going to have all the elements that are less than or equal to V, or less than or equal to the pivot. The second group, which we'll call S2, is going to contain all the elements that are greater than or equal to V, or greater than or equal to the pivot. So what we're saying here is we pick our pivot, and then all the other elements that are less than or equal to V will go into one group, and then all the elements that are greater than or equal to V or the pivot will go into the other group. So once we've done this partitioning, the last step is we're going to compute quicksort for both S1 and S2. So our result, our output, is going to be the result of doing quicksort on S1, then followed by V, the pivot, then followed by the result of doing quicksort onto S2. And that should, not just should, but it will give us a sorted array. Now the question comes, what do we do with the elements equal to the pivot? Because we said here that we put elements that are less than or equal to the pivot in S1 and elements that are greater than or equal to the pivot in S2. So where do we put the elements that are equal to? Do we put them in S1 or S2? And that actually is just up to the programmer. It's a design decision. Let's do an example of quicksort. So let's say our array is S, where S is going to be 13, 81, 92, 43, 65, 31, 57, 26, 75, and 0. And let's just suppose that 65 is our pivot. We're not going to worry right now how we pick the pivot. We'll get to that in just a little bit. But let's just suppose 65 is the pivot. So what we're going to do is we need to partition S into 2 sets, S1 and S2. So S1 is going to contain all the elements that are less than or equal to 65. And S2 is going to contain all the elements that are greater than or equal to 65. Now we're dealing with the other elements. So the 65, the pivot itself, is not going to be in either one of these sets. So in this case, S1 is going to be 13, 43, 31, 57, 26, and 0. All of them are less than or equal to 65. And then S2 is going to have 81, 92, and 75. All those are greater than or equal to 65. We'll then run quicksort on both S1 and S2. So if we just keep repeating this where we'll pick a pivot and partition and so forth, eventually when we get back, we'll have that S1 is actually 0, 13, 26, 31, 43, and 57. And S2 would be 75, 81, and 92. So eventually S1 and S2 will be sorted with respect to those sets. So then our result is just going to be S1, all of S1, and then 65, and then all of S2. So our final result would be 0, 13, 26, 31, 43, 57, and then 65, and then 75, 81, and 92. So the question we have to ask is, why is this faster than merge sort? I mean, it doesn't really seem like it's any faster because we're going to recursively solve two subproblems, and that means when we combine them, it's going to require linear extra work. So that sounds like merge sort. And technically, to make even matters worse, we're not even guaranteed that these subproblems are supposed to be of equal size. With merge sort, we're splitting the array into two equal halves, and then we keep splitting into two equal halves. Here, we're not guaranteed that. So why is this better than merge sort? Well, what we find is we can partition the elements very efficiently. So we're going to be using a very neat partitioning algorithm, and this is just going to more than make up any issues with the lack of equal-sized recursive calls. So this will take care of making up any of the differences in the sizes. So that's where we get the benefit or the efficiency improvement of this algorithm. We'll now discuss how we go about picking the pivot for quicksort. The efficiency of quicksort heavily depends on how we pick the pivot. Because if we pick a good pivot, then quicksort's going to be very fast. We're going to get that O of n log n time result if we pick a good pivot. But if we pick a bad pivot, what we would see is quicksort would actually take O of n squared time. So we want to make sure we pick a good pivot. One approach we could use for picking the pivot is just pick the first element. Let that be the pivot. In fact, this is actually a pretty popular choice. Now, here's the thing if we use the first element. If all the elements in the array are random, this is fine. So if our input is random, we don't have any issues with this. However, if the input is pre-sorted or it's in reverse order, this is going to be a disaster. So let me explain why. So what could happen is all of the elements, the other elements could go into either S1 or all the other elements could go into S2. So what you have is one set with absolutely nothing in it, and the other set has everything else in it. And if this happens enough, where we keep putting all the elements in one of the two sets, then quicksort is going to take quadratic time. So what we find here is picking the first element is actually a horrible idea. So don't do that. Don't pick the first element as the pivot. Another option is to just randomly select the pivot. And this is actually a much safer option than picking just the first element. Even if the array is sorted and we randomly pick an element, we're very likely to not pick a bad pivot. So we're very unlikely to get that bad pivot if we do random selection. Now, the one issue with random selection is that there's extra time that we need in order to pick the random element. I mean, we have to add some extra code to do that random selection. However, it doesn't affect the running time itself. So we could do this, and with high probability it'll work. We will have a good pivot, but there's just a little extra time that's needed to make that happen. There is a third option, and this is what we call the median of 3 partitioning. So let me explain how this works. The best pivot choice, the absolute best pivot choice, would be the median of the array. That way, exactly half of the elements will go into S1, the other half of the elements will go into S2. There's a problem with trying to compute the median of the array. Well, to get the median, we need to sort the array first. It's a little hard to calculate the median without sorting the array, but we're trying to sort the array. So we're saying to get the median, in order to sort the array, we have to sort the array first. So this doesn't quite work the way we want to do. So a good estimate of the median is we'll randomly select 3 elements, and we'll take the median of those 3. And what's nice about this is if we pick the median of these 3 elements, there's absolutely no way we can pick the smallest or largest elements of the array. Can't happen. Now we might pick something that's close, but we cannot pick the absolute smallest or absolute largest element. But the one issue with this is we still have this random selection problem. We still have this extra time that's needed to randomly select the 3 elements. So what we're going to do instead is we'll take the first element of the array, the middle element of the array and the last element of the array and take the median of those three. That's close enough where we still will not be able to get the absolute first or smallest or absolute largest elements, but we can pick an element without doing the randomization. Let's do an example of the median of three partitioning. So let's say our array is as follows. So we have 8, 1, 4, 9, 6, 3, 5, 2, 7, 0. So we want to take the median of the first, middle, and last elements of the array. Well, our first element is going to be 8. That's pretty clear. What about the middle element? Well, we're going to take the left and the right, divide it by 2, and take the floor of it. So we find in this case that the middle element here is actually 6. And then our last element is 0. So we just take the median of those three, and in this case, our pivot is going to be 6. And as I mentioned before, what's nice about this is we eliminate the worst case scenarios because we know that we cannot pick the smallest element and we cannot pick the largest element as the pivots. We just can't do that. Like I said, we might get something that's close, but there is absolutely no way we could pick the smallest or largest element to be the pivot.